So with these lessons, you can unmute at any time. You can actually stay unmuted if you want. So you can ask questions or make comments or whatever. All right, so this is like physics 12 is a lot of forces. Every unit deals with forces. Well, I guess this one could technically deal with forces as well. And so it's really, really important that we're good with vectors and free body diagrams and things like that. So this is a pretty important lesson. We asked some college professors, a group of physics teachers, what was most important, what they wanted their kids to come to university with. And they said the ability to manipulate vectors and draw free body diagrams. Those are the two most important things. So that's why we're dealing with this. So a vector, hopefully you know this, is a type of measurement that has both magnitude and direction. And so we use arrows to indicate vectors, and the size of the arrow is kind of magnitude, and the direction of the arrow obviously is direction. So it's a good representation of magnitude and direction. In terms of direction, and I'm going to ask for input. What would you say that is? What direction is that? Go ahead and pipe in. Anyone can talk. Spread. Nobody knows what direction that is.
East.
East? Anyone else? Can we define it as anything other than east? Awesome. Okay. So yes, east, we can also call it right, because it's going to the right. And like we're dealing with two-dimensional vectors right now, but eventually, like if we do get to electromagnetism occurs in 3 dimensions. And so then you have like up the page, to the right, down the page, and then out of the page into the page. So it gets a little bit more confusing. So for now, we're just going to deal with 2 dimensions. And if you orient your paper like in front of you, if you draw it like I just drew, that's to the right. Obviously, that's to the left or west. Okay, so just keep in mind that we're dealing with mainly north, east, south, west. Okay, they're called cardinal directions. So that's kind of what we're going to be using. And looks like a W. There we go. Okay, so that's good. What happens if we, like, if I said, okay, what's this arrow? What direction is that? Anyone?
Northeast.
Northeast? Okay. Anybody have any other? Okay, so if that's northeast, what's that? Let me draw that a little bit better. What's that? Is it also northeast?
Yes.
Right? Okay. Yes, but it's not, those aren't in the same direction, so we can't call both of them northeast, right? And so some people will say, well, that's like northeast or some combination of them. Well, when we have vectors going in 2 directions, like we have the east, left, west, right, up, down, whatever. If it's going in 2 directions, so northeast, then we need to figure out a way to indicate which way it's going. And so if you draw your northeast, west, south, northeast, southwest, and then draw an angle at either direction. So I'm going to draw an angle right here, theta. Okay, I'm gonna do the same thing right here. Okay, theta. Notice how this theta is bigger than this theta. It's more of an angle. It's closer to the north than it is to the east. Okay. And so in order to determine which way directions are going, we would say that this arrow right here is headed theta. So whatever that is, 30 degrees, 20 degrees, whatever it is. So theta degrees north of east. Okay. Now think about this, north of east. So if I start east and I go north of that, I start going that way. Okay, this is specifically north of east. Well, I'm taking my arrow and I'm rotating it that way, up towards the north. And that's how I'm figuring out that angle that I drew is north of east. It's created by traveling north from east. Okay, so if I were to say something like, let's say 40 degrees south of west. Well, south of west, so which way is west? West is this way. Which way is south of that? Well, south is that way. So that means I'm going south of west 40 degrees. So I start here and I go 40 degrees south of that. So this would be 40 degrees. And this arrow right here is 40 degrees south of west. Okay, does that make sense? The other way of saying, like, so 40 degrees south of west would be the exact same thing as 50 degrees west of south. Okay, so you can rotate from either direction to get the exact same arrow, and it doesn't matter which one you put because it's the same direction. Whether you write 40 degrees south of west or 50 degrees west of south, it doesn't matter. Okay, it's the same direction. So yeah, that's what we're working with. So then if what are we working here? If you have something like, so a typical vector would be like, let's say it's 14 newtons. Oh, my ends suck. And then let's just use 30 degrees north of west. Okay. So go ahead and draw that. What do you think that looks like? 14 degrees, 30 degrees north of west. And so you should be coming up with something that looks like that. Sure, let's call it 30. Okay. And this is 30 degrees right here. Now this is the west part, and this is the north part. Okay, so what you're actually creating is a triangle. If a force is going 14 newtons, 30 degrees north of west, what it's doing is it's being applied to the west and to the north. And because vectors can be broken down into triangles, you can actually break them into their components. And so I would say, so this is my force right here, right? So measured in newtons, so this is a force. Well, this force, because it's in two directions, can be broken into Fx and Fy. And Fx would be equal to 14 cos 30. Okay, you use trig. Okay, Fx is adjacent to the 30. 14 is hypotenuse, so that's cosine. Cosine of 30 is adjacent of hypotenuse. Solve for adjacent. Fx is 14 cos 30. And then Fy would be 14 sine 30. Okay, and you can break it into components. And so then I would take my calculator and I'd go 14 cos 30, making sure that's in degrees, not radians. This is 12.12 newtons. Notice how I'm not worrying about sig figs at all. And this is 7 newtons. Now the next part I need to do, and there's a direction I left off when I did these things up here, east, right, and there's one more that we could define it as. Does anyone know? No. Okay, so the last one, anything going to the right is positive. Anything going to the left is negative. And the same thing with up, down. Up is positive, down is negative. And so I would look at my force and say, okay, the Fx is going in the west direction, so that's to the left, so that would be negative 12.12 newtons. And my Fy is going up, so that'd be positive 7 newtons. Okay, so that's another way of doing that. And we'll get to that when we start adding vectors together. Okay, so the next part is adding and subtracting vectors. So let's add first. So a man bikes 13 meters east and then 20 meters west. What is his final displacement? So this is actually probably a pretty easy question to do. You could probably do it right now without my help. And what you're doing is vector addition. So you're instinctively doing it. And if things get difficult, just go back to instinct, because that's what you're going to do. So obviously, if the man bikes 13 meters east, he's going to go that way, 13 meters, and then 20 meters west. Okay, so from his starting point to his intermediate point, we're 13 meters to the east, and then he goes west 20 meters that way. Okay, 20 meters. What is his final displacement? Now I'm asking for displacement, which is not distance. Distance is a scalar measurement that takes into account the total path. So the distance would be 33 meters, okay, because it's 13 plus 20. But the final displacement is a measure from where he starts to where he ends, okay? And so the vector addition, we have one vector here, so let's call this vector A and vector B. When we add them, all you're doing is you're drawing vector A and adding vector B to vector A. Okay, so it looks like this. VA plus VB. You're adding it to, you're starting VB at the end of VA. Okay, instinctively, that's what you should be doing. Now, if this is 13 meters and this is 20 meters, the end part or whatever from start to finish is going to be -7 meters. Okay, notice how I'm making it negative because he's ending to the left of his original position. Okay, so then we would say D equals -7 meters. Or if we want to put it into the same format that the question puts it in, we would say 7 meters west would be his final displacement. Okay, now let's apply that to this one now. So that the girl walks 14 meters west, so that's your VA, and then 32 meters north, that's VB. So what we're doing is finding her final displacement, which is going to be VA plus VB, VA plus VB. Okay, and so we draw VA, which is that 14 meters. This is a little bit bigger. And we're adding to that VB, 32 meters north. So we're starting at the end of VA and we're drawing VB, 32 meters. That should be a little bit bigger because let's make this a little bit bigger. 32 is significantly bigger than 14. So we should try to draw it as to scale as possible. I'm not going to draw it perfectly to scale or anything. And then the final displacement, so this is the start, this is the end, okay, is going to be the arrow from the start to the end. It's kind of like the outcome of your vector addition. Now, if you notice this, we have created a triangle. So we can't just use simple arithmetic like we did in the first example. You have to use trig. And so this is a right triangle. We prove that because it's west and north. Okay, you can never assume it. You have to be sure. West and north are always 90 degrees to each other, so that's 90 degrees, which means we can use Pythagorean theorem to find the final displacement. So the final displacement will be 32 squared plus 14 squared, and then square root that. Which is 30, let's just call it 5 meters. So this is 35 meters. And So that's the magnitude of our displacement. But that doesn't answer the question, what is the displacement? Because displacement is a vector, which means we need direction on that. And so to find direction, we need to figure out how to define the direction of this arrow right here. Okay. Now think about this. The girl walks 14 meters west and then north of that. So I already know that it's going to be some angle north of west. Okay, because she's walking north of her west position. And so that angle north of west is right here, this angle right here. Okay, that's formed by going north of west, that angle right there. And so now I can just apply the correct trig formula, which I'm going to use tan. Tan theta equals opposite, 32 over adjacent, 14. 32 over 14. Second tan, answer. And you get 66 degrees. Oops. Come on, pen. 66 degrees north of west. Okay. Hopefully that makes sense. Any questions so far? Hopefully you've done some of this before. I teach some of this in Physics 11, so hopefully your teachers do too. Okay, so summary, how to add vectors. You draw your first vector as an arrow, obviously, and then you draw your second vector starting at the point of the first vector. So you have the point of the first vector is that the tip of the arrow. And so all you're doing is you're drawing the second arrow coming from the first arrow. And then the answer is a line drawn from the start of the first vector. So like, for example, if I had, let's say A and B, A plus B would be A plus B, like that. And the answer would be that arrow right there. Now notice how if I change this to B plus A, it'll get the same thing because then I'm starting with B and then I'm adding A. And my arrow, like this arrow, is the same as this arrow. It's the same answer. Okay, so that rule of adding still applies to this scenario, where it doesn't matter the order you add in. Subtraction's different. We'll get to that in a sec. Okay, so the stuff we've done already is fairly simple because it's all right triangles. Now we're going to deal with non-right triangles, and this is where I start to lose kids, but hopefully we'll be on the same page. There's two methods to solving these, and I'll teach you both, and then we'll determine which one you want to use. It doesn't matter which one you use on a test or anything. I won't dock marks for using one or the other. I definitely have my preferred method, and you don't have to do it that way. So a boat travels 14 kilometers, 22 degrees north of east, and then 8 kilometers, 40 degrees south of east. What is its final displacement? So let's say the starting point is right here. It's going to go 14 kilometers, 22 degrees north of east. So that's something like, I'm going to draw this a little bit bigger than normal. This is 22 degrees, that angle right there. And this is 14 kilometers. Okay, and then 8 kilometers, 40 degrees south of east. So that's going to look like, so from that point, you're going to go 40 kilometers. So like at every point, you can always imagine there being an origin, kind of like a northeast, southwest origin. And so from that point, we're going to draw another vector, which is 40 degrees south of east. So that's east going south of that. So that's going to be something like that. And now this is only 8 kilometers, so I'm not going to draw it quite as long as the 14. So there you go. This is 40 degrees right here, and this is 8 kilometers. Okay. Now, the first method is called component method, and that's because we're going to break these vectors into components. I should have drawn these in different colors, but that's okay. I'll start now. So The component method deals with breaking into components. So if you think about every vector being some x, some y, then you can break it into, this is going to be the first one, the x. Let's call this D1 and D2. So this will be D1x. Okay, and then this one, I drew that a little bit too long, but that's okay, is going to be D1y. And because it's xy, this is 90 degrees right here. Okay, and so we'll leave it at that for a sec. And then we'll draw the next one. So the next one, going green, is going to be D2x and D2y, like that. Okay, so all you're doing is you're drawing a right triangle on each vector. You're breaking it into its components. Now, here's how it works. So if D final equals D1 plus D2, okay, because that's what we're doing, we're finding the final displacement by adding two vectors together, then if you break it into components, dfx will equal d1x plus d2x, and dfy will equal d1y plus d2y, like that. Okay, so if that's the case, what we can do is we can add d1x plus d2x to find dfx. Like we're finding, let's change the color again. We're finding this vector right here. That's df. Oh, that's a terrible vector. That's okay. And so that's like, if you think about that vector, it's gonna, and I'm not sure which way it's going, but that's okay. This is its dx, so that's dfx, and this is dfy, like that. Okay, so that's what we're finding. And so dfx is going to be the sum of both x's, so we'll find that right now. dfx is going to be d1x plus, I already wrote that, I don't need to write it again. So d1x is a component of the first vector, so that's going to be, it's adjacent to the angle 22 degrees, and we have the hypotenuse, so we're going to use cosine. And so if you go like cos 22 equals d1x over 14, and so you can solve that by going d1x equals 14 cos 22, 14 cos 22, okay, plus, and notice how this is positive because it's going to the right. d2x is also going to the right, so it's positive, it's plus. This is going to be 8 cos 40. Okay, like that. And then if you solve that, 14 cos 22 plus 8 cos 40, that's going to equal 19.1, and we're dealing with kilometers, so that's kilometers. Okay, and then dfy is going to equal d1y plus d2y. So d1y is going to be 14 sine 22. So we're dealing with sine now because now it's opposite to my angle. And then plus, because we're adding vectors, negative 8 sine 40. Now, why is that negative? Because d2y is going down. It's going south. And so we're subtracting it because it's going the opposite direction. Okay, so that's why we're drawing all of these individual arrows. This one's going to the right, so it's positive. This one's positive. This one's positive. This one's negative because it's going down. Okay, so now we're going to go 14 sine 22 equals, and then plus minus, it's just minus, so minus 8 sine 40. And that is 0.102, so just 0.1 kilometers. Okay, so that's drawn fairly to scale. Okay, so then, now that we have dfx and dfy, we just draw that out. So dfx is 19.1, so that's going to be like that, 19.1. And DFY is 0.1, so that's very, very small, 0.1. And then we're going to solve the hypotenuse. And that's all we're going to do. So DFY is going to be 19.1 squared plus 0.1 squared. Square root is probably going to be 19.1 anyways. Yeah, 19.1. I totally random guessed at the numbers, and it kind of cancels out both y vectors, so that works out pretty well. And then, like, what I mean by that is 14 sine 22 is 5.24, and 8 sine 40 is 5.14. Oops, forgot the one. So like those are pretty much the same thing. And so because both y's are kind of canceling out, you could probably just say, like, this angle is going to be tiny. Okay, so technically I'll just solve it. DFY is 19 kilometers. I can drop the 0.1 because it's whatever. And then to find that angle, I'm going to go tan. So tan theta is 0.1 over 19.1. So it's going to be very, very small. Yeah, that's nothing. Yeah, 0.3 degrees. So I'm just going to say east. Okay. Because it's 0.3 degrees, you should, like, I kind of always round to the nearest degree when I do that. And so I'm rounding to 0 because it's 0.3. So it's just going east, and that's fine. Okay. Does that sort of make sense? Any questions? Like, feel free to jump in at any time. Okay. The next method is a closed vector diagram. And so closed vector diagram, you're going to start the same way. You're going to draw your first vector. So that's 14 degrees or 14 kilometers, 22 degrees above or north of east, and then plus your 8 kilometers, and this was 40 degrees, like that. Now, instead of breaking into components and drawing each component separately, all we're going to do, and I'm going to, because I drew it a little bit differently last time, so I'm going to draw it the same way. All you're going to do is you're going to draw this straight line, the answer, so the DF, and keep it like this. Okay. Now this, what we have now is a triangle. It's a non-right triangle, which hopefully we're good at solving. Now keep in mind that this 22 degrees here is to the horizontal. Okay, it's not that interior angle, so we don't know that yet. So you're going to have to use a little bit of geometry here to figure out angles. So this angle, I have no idea what it is. Okay. However, I know that if this is 22 degrees north of east, then this is going to be 22 degrees right here as well. Okay. And if that's true, then this angle is going to be 68 degrees. Okay, so notice how I'm drawing kind of like a what do you call it? A corner, I guess. Same thing I could do here. Okay, there's my corner. This line right here is 22 degrees, which makes this one 68 degrees. Okay, and so what I'm doing is I'm finding the angle between the vertical line here and this vector right here. And the reason I'm doing that is because I also know that this is 50 degrees. Okay, and so now I have an interior angle of my triangle, which is 118 degrees. So that angle right there is 118 degrees. Now, why did I do that? Because now I have an angle, like now I can use cosine law. Okay, so cosine law is c squared equals a squared plus b squared minus 2AB cos C, angle C. So this is angle C, that's A, that's B. This is little a, or sorry, little b, little a, little c. Okay, so you can assign those arbitrary letters to each corner of the triangle. And now we can solve for little c. Okay, and so we're going to do that by going c equals a is 8, so 8 squared plus 14 squared minus 2 times a, so 8 times 14 times cos, and the angle opposite to what I'm trying to find, so 118. And then we're going to square root that whole thing because it's c squared. Okay, if we do that, 8 squared plus 14 squared minus bracket 2 times 8 times 14 times cos 118. And then square root that. You get c equals 19.1 kilometers. Okay, and so exact same answer as before, but we're not done yet. So now that we have this side, which is 19.1, we can use sine law to find this angle right here inside the triangle. Okay, and so we're going to do that by using sine law. So we're going to go sine theta over 8 equals sine 118 over 19.1. And then you can solve for that angle. So 8 sine 118 divided by 19.1 inverse sine, and you get 21.7 degrees. Okay, now if this is 21.7, so let me draw this corner a little bit better. So we have, so remember that our original angle was 22 degrees, so this is 22 degrees. Okay, and then our DF kind of cuts it like this, right? And we found, let me draw this over here. So this is 22 degrees. This angle, which is what we just found, the interior angle of our non-right triangle, is 21.7 degrees, which means that this piece right here is 0.3 degrees, which matches what we had up here. Okay. And so you would put that in and say, okay, this is 0.3 degrees north of east, or you can just call it east if you want. Okay, so two methods to solve the exact same thing. My preference is closed vector diagram because I'm more comfortable using sine law and cosine law. But if you like right angle trigonometry and adding components, go for it. Okay, it's totally up to you. Okay, before we start vector subtraction, and please stop me if you have questions, just butt in whenever you want. Let's look at what we had before. So we had, how did I draw that again? Maybe I'll draw that. Where do I want to draw this? I'm going to draw it down here because I'm going to need that room. So let's say this is A, so vector A, and this is vector B. And keep it small. Okay. What would A plus B look like? Well, we already covered that. Okay, you go A plus B like that. Okay. Now, what would A minus B look like? Because I could go B plus A and get the exact same thing. But what would A minus B look like? Okay, and the way we do this is you need a way to subtract this from A. Okay, now think about it this way. Instead of doing vector subtraction, we're just going to do vector addition again, but we're going to do it like this. A plus negative B. Okay, it's the exact same arithmetic as A minus B, but it allows us to visualize it a little bit better. Okay, so if B is this line right here, this arrow, then negative B would be the exact same thing, but opposite direction. Okay, so if this is, let's say, 30 degrees west of north, then this one would be 30 degrees opposite of west is east, opposite of north is south. Okay, so exact opposite. So A minus B would look like this. A minus B. You're just adding B to A, but you're just flipping B. That's all you're doing. Okay. Now, in addition, the direction you do this in doesn't matter. A plus B, B plus A, exact same thing. In subtraction, it's not the exact same thing. A minus B is very different than B minus A. Okay, it's the same thing as, like, imagine A was 2 and B was 1. 2 plus 1 is the same thing as 1 plus 2. 2 minus 1 is not the same thing as 1 minus 2. Okay, and so very different answers. Okay, so an airplane's flying at 430 kilometers an hour, 32 degrees west, and blah, 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 changes its velocity. So what is its change in velocity? So in this one, what we're dealing with is anytime there's a change in something, so change in velocity, delta V, delta's change in, it's final minus initial. So change in velocity is VF minus VI, final velocity minus initial velocity. So this is our VI right here, and this is our VF right here. Okay, so if we're going to do this in a vector subtraction, what we need to do is draw VF first, okay, because it's VF minus VI. So we draw that first, and that's 488, 12 degrees east of north. So that's going to be something like, which way is that one going to go? It's going to go east of south, so that's that way, so I'll draw it over here. So it's something like that, okay, and I'll keep it nice and big, I guess. So this is 12 degrees, and this is 488, which is on the wrong side, okay, kilometers per hour. And then to that, because we're not going to do VF minus VI, we're actually doing VF plus negative VI. Okay, we're going to take VI, which used to be west of north, but we're going to deal with negative VI. So negative VI is equal to 430 kilometers an hour, 32 degrees south of east. Okay, it's going the other way. So we're going to add this vector to our first vector. So we're going to go 32 degrees south of east. So that's something like that. 430. So not quite as long, but still, it's pretty close to the same. And so this is 430. This angle right here is 32 degrees. And the answer, what we're trying to find, the delta V, is this right here. Okay, this is your delta V. So if you want to use components, what you would do, and I'm going to just show you how to break it into components. I'm not actually going to solve each one. So this would be your VFY, and it's positive because it's going up. And then to the right, this is your VFX. And then to that, you're adding VIX. And then you're going to take your negative VIY away from your VFY. Okay, so that's how you would do that part. I'm not going to actually solve it though. Okay, so I'm gonna go ahead and solve it using the closed vector diagram. So I have 12 degrees right here, which means that this is also 12 degrees. And then this is 58 degrees. Okay, because this, like if you think about this as being a T, okay, where it's all perpendicular, if this corner right here is 12, this corner also has to be 12. That's called the Z rule. I don't know if you guys remember that, but if you have a Z where you have two parallel lines intersected, then this angle is equal to that angle, and that angle is equal to that angle, I guess. And because I'm comparing it to the y-axis in both cases, then those are obviously parallel lines. So that's how I know that if this is 12, this is 12. And then this one is obviously a right angle. So 32 degrees, 90 minus 32, 58. So then that gives me this as 70 degrees. Okay. And so now I can solve for my delta V using the cosine law. So delta V is going to equal, doesn't matter which one's A or not. Why is this 430 degrees? That's weird. Okay, 430 squared plus 488 squared minus 2 times 430 times 4088 cos 70. And then we're going to square root that whole thing. So to do that, just plug it into your calculator. 30 times 488 cos 70. Okay, so that gives us a value of 530 kilometers per hour. And then we need the angle or the direction. So what I want to do is I want to find the angle formed inside of the triangle that I'm dealing with. So that, like, obviously it's the black triangle that I drew here. So I want to find this theta right here. Okay, so I'm going to go sine theta over 430 equals sine 70 over the answer I just got, 5. And I'm going to use the unrounded value just to get, actually it doesn't really matter. These values are big enough that it's not going to make a difference. So solving for theta, 430 sine 70 divided by 530 equals that, second sine that. Okay, so that's theta is, let's just call it 50 degrees. Okay, 49.7, 50 degrees. So that means this is 50 degrees, but that still doesn't give me my direction. Okay, that's not, that 50 degrees is just that angle in between in my non-right triangle. I need to relate it to either south, west, north, or east. And so if I add these two together, 12 plus 50, I get 62. And so if I could either say it's 62 degrees, sure, 62 degrees east of north. Okay, because that's north. You go 62 degrees, you get to this line right here. And that's the direction of delta V. Or you could say, okay, 90 minus 62 and express it as 28 degrees north of east. Either way, it's the same direction. Okay, so that's about it. Does anybody want me to break down the vectors, the VFY, VFX, all those, the components? Just say yes and I'll do it. No? Okay, if you want to do it the vector way or the component way, just do it and compare your answer to mine. If it's different, then just ask me and I'll go over it with you. So that is it for this lesson. So now you can go to the Files tab and work on the worksheet. And that's it for today. So I won't bother you anymore today. We're done for today. You can message me. I'm actually busy this afternoon, but within the next hour, you can message me with any questions. Otherwise, I will see you guys all at 8:30 tomorrow morning for the next lesson. And that's it. Okay, have a great day.
Thank you.
Thank you.